Hey folks, my name is Nathan Johnson. Welcome to Lecture 19 of Vector Calculus, where we're finally going to prove Green's theorem, or at least we're mostly going to prove Green's theorem, okay? We're going to prove it for a class of regions that is generally enough to cover everything that we're going to do in this course, and probably generally enough to cover every application of Green's theorem that you're going to use even beyond this course. But it is worth knowing that, Green's theorem, it's slightly more general than the proof here applies to. It does apply to slightly uglier regions than we'll consider here. But whatever, let's just see the key ideas that go into the proof of the Green's theorem, and we'll sort of sweep some technicalities under the rug at the end, okay? So let's start off by proving Green's theorem for regions that we're going to call bisimple, okay? What a bisimple region is it's a region where you can define it in terms of a bottom curve and a top curve, or also in terms of a left curve and a right curve, okay? So for example, over here, this is an example of a bisimple region, because I can define it in terms of, well, there's a bottom curve, gamma of x, and there's a top curve, delta of x. But also I could equivalently say, okay, that exact same region, it has a left curve, what I'm going to call alpha of y, and a right curve, beta of y, okay? And that's all these descriptions up here describe. It says, it's all points in the plane, all xy coordinates, where the y value is going between a bottom curve and a top curve, and then the x values are just going between whatever the leftmost x value is and whatever the rightmost value is. Or equivalently, it's also, x is going between a left curve and a right curve, and the y value is going between, a bottom value and a top value, okay? As long as it has two separate descriptions, one in terms of top bottom and one in terms of left right, yeah, that's a bisimple region. Okay, and sort of geometrically what this corresponds to is it's a region where if I sliced it with a vertical line, that vertical line is going to go through the boundary at two spots. Okay, no matter where the vertical line is, except maybe only at one spot, that's fine too. Okay, and similarly, if I slice it with a horizontal line, it's going to go through either 0 times or 1 time or 2 times. Okay, as long as it has those two properties, kind of like a modified version of like a vertical and horizontal line test, yeah, that's what we're calling a bisimple region. Okay, and it turns out these regions are sort of the simplest ones to prove Green's theorem for, because this flexibility of switching between, like a top and bottom description over to a left and right description, that flexibility there gives you some way of showing, oh, this integral equals this integral over here, and you can make Green's theorem pop out. Okay, so let's see how it works for these types of regions first, and then we'll start generalizing to more exotic regions that don't have nice descriptions like this. Okay, and maybe before I even get onto that, okay, I want to emphasize here that I'm going to start off by computing the vector line integral around this region. I'm going to be trying to come up with sort of an explicit formula for that. But actually, even before I do that, I'm not going to be computing the entire vector line integral. I'm going to be computing kind of like the first half of the vector line integral. Remember, the vector line integral around a curve, one way you can write that is in what we call differential form, okay? So you can write as the integral over the curve of f1 dx plus f2 dy. I'm going to ignore the f2 dy part just for a little bit, okay? I'm going to start off, just compute the integral of f1 dx. What does that get me? I'm going to come up with a formula for that, and then we'll talk about f2 dy in a second, okay? So how can I come up with a formula for this? Well, just, pick your top-bottom description or your left-right description. I'm going to do the top-bottom description, okay? So what I'm going to do is I'm going to parameterize the bottom curve, right? This y equals gamma of x. Our usual way of parameterizing that is you just say, okay, x equals t, then y is gamma of t now, okay? And where's t going from? Well, the left point to the right point, so t is going from a to b. Okay, so this curve here parameterizes the bottom of the region. Well, I better parameterize the top of the region as well, so that when I integrate, I go around the entire boundary. Okay, so the top, it's going to be parameterized in the exact same way. The only difference is it's not gamma of t anymore. Now it's delta of t, because that's my top curve. Okay, and then how do I compute, this integral here, this integral of f1 dx? Okay, well, I plug into my formula for vector line integrals, right? Remember dx, think of that, like you have to turn it into an integral with respect to dt. So what I'm going to do is I'm going to, plug my parameterizations, this f of t and this g of t, into f of 1, and then I'm going to have to do a little change of variables. Like, what does dx become? Well, fortunately, it's just going to become dt, because my x-coordinate is the dt coordinate, right? dx by dt is just 1. So when I do the little change of variables to turn dx into dt, it just becomes dt directly. what gets plugged in here where I've got xy is, well, just plug in your parameterization, plug in your path. So I plug in t gamma of t in here and t delta of t down here, okay? And I need a sum of two integrals because I don't want to just integrate along the bottom curve, right? I want to integrate all the way around, okay? Bottom curve and then top curve, okay? So I've got to add up these two integrals. And then I've got to be a little bit careful here. I don't actually add them, I subtract the second one, because if I look at this orientation, this G here, okay, this top curve, well, with the way I've parameterized that, with t going from A to B, it's going to parameterize it this way. It's going to parameterize it going clockwise, whereas I said I'm going to integrate here with the curve oriented counterclockwise. Okay, so the bottom curve's fine. That's going counterclockwise around the region. But then I've got to subtract the part of the integral that's coming from this top curve because I parameterized it backwards. Okay? All right. All right, so fine. Okay, so that's, sort of my first half of the vector line integral. The integral of f1 dx equals this very concrete integral over here involving the real variable t. Okay, well, if I did that exact same computation for the second half of the vector line integral, so now the integral over the same curve, but f2 dy this time, well, this time what I'm going to do is I'm going to do that in terms of left and right curves, not bottom and top curves. I'm going to do, left curve and right curve. And if I do this exact same stuff that I did up here, I'm going to get this formula for the integral of f2 dy. Okay, so it's just going to be the integral with, the right curve plugged in minus the integral with the left curve plugged in. And again, the reason the sign is swapped in between is just because if I parameterize them in this way, well, they're both going from bottom to top around the edge of the region, and I don't want that. I need them both going counterclockwise. So I need, the beta curve, the right curve going up, but then the alpha curve going down. And that's what this negative sign here accomplishes. Okay, and now focus on, I've got this term here and this term here. If I add those up, I'm going to get the vector line integral around the entire boundary, right? Because the integral of f1 dx plus f2 dy, that's the vector line integral around the entire boundary. Okay, so I'm just going to write that down now. Okay, the vector line integral around the whole boundary, it's just the sum of these previous two things, which, I mean, it's just this big, long, ugly expression. This is just copy and pasted from up above. Okay. Fine. I've got the vector line integral around the region equals this chunk here. If I could show that the double integral over the region equals the exact same thing, then yay, I'm done. I've got Green's theorem, right? I've got, left-hand side equals right-hand side. Okay, so now that's what I'm going to try to do. I'm going to switch gears and say, okay, this double integral here, can I show that it equals this exact same expression? Hope so. That'd be nice. Okay, so let's try to do that. And again, I'm going to split it up into sort of smaller chunks here. Okay, I'm going to start off just by doing the double integral of this first piece, del f2 by del x. Okay, and when I do that, okay, how do I compute a double integral? Well, I have freedom. I can do the x integral first and then the y integral, or vice versa. I'm going to do the x integral first, and sort of my reasoning, my rationale is it kind of looks like the dx's and del x's, those will kind of cancel out. Like really, it's going to be the fundamental theorem of calculus that takes care of this for me. But that's sort of the high level idea here is like, oh, maybe I'll be able to cancel those out and just get an f2 on the inside here if I do the x integral first. Okay, so anyway, what's y going between? Y is going between its lowest value, which was c, and its highest value, which was d. Okay, and what's x going between? It's going between the left curve, alpha of y, and the right curve, beta of y. Okay, and now I'm just going to apply the fundamental theorem of calculus. Okay, when I integrate some function with respect to x, I just get an x antiderivative of this function here. Okay, I just get f2 back itself, right? Because like to get del f2 by del x, I took the x derivative, treated y as a constant, and then when I integrate with respect to x, I do the exact same thing backwards, right? I just, find an x antiderivative and again treat y as a constant. Okay, so all I get is f2 with the endpoints plugged in, beta of y, alpha of y, subtracted, because that's how the fundamental theorem of calculus works, right? You subtract with the endpoints plugged into the antiderivative. And in the y coordinate, it's just y, which has been held constant this entire time. Okay, and I'm just left with the y antiderivative, or the y indefinite, or sorry, the y definite integral on the outside of that whole thing. So I apply the fundamental theorem of calculus to this inner integral here. Okay, if you do the exact same thing with negative del f1 by del y, you get something similar happening, except instead of using like a left curve and a right curve, we're going to use a bottom curve and a top curve. Okay, and this time what happens is, well, you get this expression here. Again, you're applying the fundamental theorem of calculus to this stuff on the inside. This time I'm applying it to like the y variable. I'm going to do the y integral first, apply the fundamental theorem of calculus, and I get this expression right here. Okay, and now I just squint really, really hard at what I've got, because I've basically got Green's theorem at this point. Okay, if I go back up to, like, what did I have? The vector line integral equaled this horrific junk right here. Okay, but let's focus on the second junk. Okay, it's an integral from c to d of f of beta of tt minus f2 of alpha of tt. That's exactly what I've got here. The only difference is what I called t up here is called y down here. But I mean, they're just real numbers. It doesn't matter what the variable of integration is called. This integral right here equals this integral over here. Okay, and similarly, this first one, an integral where t is going from a to b, and I've got t gamma, t delta. Oh, that's exactly this. Here it's x is going from a to b, but then I got x gamma minus x delta. That's the same thing. The only difference is that the name of the variable of integration, it's not called t anymore, it's called x. Okay, but the point is, if I add up these two integrals, yeah, I get exactly this vector line integral, and that's all Green's theorem told us. Okay, so yeah, the sum of these two double integrals here equals the vector line integral, and that gives us Green's theorem. Okay, that's it. That's Green's theorem for bisimple regions. Okay, regions that have these really nice descriptions in terms of bottom curves and top curves, and also left curves and right curves. Okay, what if your region's a little bit uglier? Okay, what if your region's not bisimple? So for example, what if you had a region that looks something like this? This is not bisimple, right? Because there's not a left curve and right curve or top curve and bottom curve, right? I mean, it's like, oh yeah, there's a top curve, but no. Like, is this the bottom curve? And then there's another top curve and another, like, no. That's not what we mean by bisimple. There's not a single top and bottom curve and a single left and right curve. Or I mean, equivalently, like, if I slice with a vertical line, does it cross the boundary just twice? No, it crossed at 4 different spots. And same with left and right curves, right? I mean, it's crossing the boundary too much. This is not a bisimple region. So what can we do here? How can we leech off of things that we did up above to still try to prove Green's theorem? Okay, and the trick is split up this region into bisimple regions. And this is one of the details that we're glossing over here. I'm not going to try to convince you that you can always do this, okay? I'm not going to try to convince you that, like, no matter which ugly region that satisfies the hypotheses of Green's theorem, you can always split it up into bisimple regions. No, I'm not going to try to convince you of that. So that's one of the details we're glossing over here, okay? But if you can do this, if you can split up your big region D into smaller regions that are themselves bisimple, and furthermore, only overlap 2 boundaries at a time. So for example, this region D1 here, yeah, okay, there's a boundary overlapping with D3. There's no more overlaps there. Like, it's not like D2 and D4 are also overlapping on this region. And similarly over here, yeah, the boundaries of D1 and D2, they're overlapping here. But, you know, they're never overlapping more than 2 at a time. 2 of these subregions have an overlapping boundary there, but there's not like D3 and D4 are also overlapping at the same spot. Okay, so as long as you can split it up into bisimple regions where it's just 2 of the subregions have overlapping boundaries at a time, then it turns out things are going to be okay. Okay, and how does this work? Okay, well, the trick is, what I'm going to do is I'm going to say, okay, well, C1 is the counterclockwise boundary of D1, and then C2 is the counterclockwise boundary of D2, and so on. And then, well, the double integral over the entire region D, right? The double integral over this whole big thing is just going to be a sum of a bunch of smaller double integrals, right? It's going to be the double integral over the first region, plus the double integral over the second region, plus the double integral over the third region, and then the fourth region, and so on. And in general, if there are n regions, then just the double integral over the whole thing, it's just going to be the sum of n double integrals, one for each of the subregions, one for each of the pieces that you split up the whole thing into. Okay, and then because these regions, D1 up to Dn, those are bisimple, well, we know from our proof up above that each of these double integrals, each of these smaller double integrals here, is equal to a vector line integral around the boundary of that smaller region. So for example, you know, if I want to compute, the double integral of that del f2 by del x minus del f1 by del y on this region D3, I can just do the counterclockwise vector line integral on that region. And same for all four of those regions here. Okay, so this is true. We've already proved this. The double integral over the whole thing is the sum of these vector line integrals. Okay, it's super duper tempting to say, okay, well, the sum of these vector line integrals here is just the vector line integral around the whole boundary. And that's almost true, but there's a little bit of a wrinkle here. And the wrinkle is that if you take the union of these smaller boundary curves, you don't get the bigger boundary curve, right? And that's maybe a problem, right? The boundaries overlap, remember. Okay, what we're calling C1, that was the boundary of what we call D1, and that overlaps with C2. It overlaps with the boundary of D2. So if I want to compute, the vector line integral around this boundary, like, why is it okay? Like, is it okay? It's not obviously okay that I can just integrate around these four, subcurves, because they're not really subcurves. They have extra lines drawn on them. I don't want this region here because that's not part of the actual boundary of D. Okay, so what's the fix here? How do we sort of make the leap and say that, yeah, the sum of these vector line integrals really is this one vector line integral around the boundary of D itself, okay? And the trick is to, like, when you analyze these overlaps, okay, when you analyze, like, where C1 overlaps with C2, for example, you'll notice that if we parameterized each of these subcurves going counterclockwise, then these overlaps are always going in the opposite direction of each other, right? So, like, for example, on this line here, C1 is going up, C2 is going down. Okay, so when I compute these two vector line integrals, 1 over C1 and 1 over C2, well, the portion that comes from this straight line segment, they're going to cancel out with each other because I'm integrating one of them upwards and one of them downwards. And that happens on every single one of these. As long as I integrate all of them counterclockwise, sort of these boundary pieces where two of the regions overlap, they're going to cancel out with each other because you integrate one of them going one way, one of them going the other way, and the total net contribution to the integral is just 0. Okay, so they come in opposite pairs. So when you integrate over these four regions, it's just the same as integrating over the boundary curve with those overlaps removed, which is just exactly what we wanted, okay? And this gives us Green's theorem now, not just for bisimple regions, but for any region that can be broken down into finitely many bisimple regions where only two of those subregions overlap at a time. Okay, and we're going to leave it there. That's good enough for us. Every region that we're going to encounter in this course can be broken down in that way. So we're convinced that Green's theorem works, for the types of regions that we're going to consider at least. Okay, so thanks for watching, everyone. I will see you next time.